Okay, let's start. Hello, everyone. Good morning. Thank you very much for joining my presentation. I know there are many other different talks, interesting talks running in parallel, so thank you for joining. We all know about global warming, about how human activities contribute to a continuous increase in temperature in all the places around the world. We all hear about the changes in climate, about how the temperature is increasing, the levels in the sea are rising, about the extreme weather conditions such as floods and hurricanes. What can we do as software engineers to help prevent climate change? What practices can we apply in our daily work to make an impact and help prevent climate change? Stay with me, and I promise you that we will see some things, some simple practical steps that you can follow in your daily job so that you can make a true difference. My name is Yannis Kolaxis. I am a software architect and a distinguished expert. I work for Atos and I am based in Greece. We have a team and we built together a software application that helps emergency services to answer emergency calls and respond to these emergency incidents, essentially empowering emergency services to save human lives. Last year, I won the first award at Atos Innovation Week for coming up with the most innovative idea, having built a proof of concept on Microsoft Azure using services like Azure Computer Vision, Azure Logic Apps, and Azure Serverless Functions. I really like learning new technologies and try to find out ways of how these technologies can help us solve problems. That's how I came up with several patents. And if you're interested to learn how you can become an inventor, you can also read one of the articles I've written in my personal blog, kolaxis.dev. And you can also follow me on Twitter to stay updated about the topics that are most interesting to me. First of all, I'd like to make sure that we all have a common understanding of the problem. What exactly is climate change? Climate change is due to the human activities, such as burning fuels, burning coal, gas, and oil, that contribute to the production of greenhouse gases like carbon dioxide and others that are present in Earth's atmosphere, trapping heat. How does this work? They actually let the sunlight to pass through the atmosphere, but then they do not let the heat associated with the sunlight to escape the atmosphere and go back to space. We can actually think of greenhouse gases as some kind of blanket wrapped around the Earth, which increase the temperature. Back in 2015, several countries and companies have gathered and made an agreement called the Paris Agreement in order to avoid climate change. The agreement, the common goal is to limit global warming to well below 2 degrees Celsius, preferably to 1.5 degrees Celsius. And the way to achieve this is by limiting the emissions of greenhouse gases such as carbon dioxide. From now on, for simplicity, we will be referring to greenhouse gases as carbon dioxide emissions or carbon emissions. Who are the key contributors when it comes to carbon emissions. According to the International Energy Agency, the top contributor are electricity and heat producers, who produced 42% of carbon emissions back in 2018. Second come the transportation, and third, the industry. As software engineers, which sector is the one closest to our work? How are we related to the top contributors of carbon dioxide? Can you guess? It's electricity. Our applications, our software applications, run on top of servers, and these servers are hosted in data centers, consuming electricity. And our clients, our customers, access our applications via a network in order to exchange data. And this data network is most commonly the internet. According to the International Energy Agency, 2% of global electricity was consumed by data centers and data networks. That's how we contribute indirectly to carbon emissions. That's how we contribute to climate change. As you can notice, data networks consume more electricity than data centers. What can we do in order to make both the data centers and the data networks more energy efficient? There are two ways that we can contribute. The first one is to apply IT for decarbonization, to come up with new, innovative business models that help us reduce carbon emission. An example is working from home, using an application like Microsoft Teams in order to collaborate with our colleagues, versus to taking our cars and commuting to the office. This is how technology can help us reduce carbon emissions. It's a simplistic example to understand what we can do. And the second way we can help is by decarbonizing IT itself. That is making our software applications more efficient, more energy efficient. In the example that we just mentioned, we would be enhancing, for example, Microsoft Teams to use a smaller resolution, a lower resolution, while having video calls, so that we do not consume too much electricity for transferring the data associated to the video calls. Today, in our presentation, our focus will be on the second topic, decarbonization for IT, how we can make our software applications more energy efficient, reducing their carbon emissions. So how can we reduce the electricity consumed by data networks? As an example, we all use our browsers to visit websites. For each website that we visit, our browser needs to download all the content of the website, like download all the photos, download the fonts and the scripts that are provided by this website in order to render the page. The more resources we have to download and the bigger the size of the photos and the fonts is, the more electricity has to be consumed by the network. One simple thing that we can do in order to reduce the energy consumed is to reduce the size of data sent over the network. So we can enhance our applications to filter out unnecessary data. Perhaps there is data exchange that is not really needed by our applications. And we can also compress the data before these are transferred. Another thing we can try is to minimize the distance that our data has to travel over the network. For example, we can pick the location in Azure of hosting our servers that is closest to our customers, to the majority of our customers, so that the number of hops from one server to the other is minimized. And there is also the strategy of placing edge servers right where the data is being produced, right at the source of data, so that data is processed locally and doesn't have to be transferred over the network to the cloud. Let's move on to another subject, the one related to highly available applications. It's very common for enterprise applications to deploy redundant servers. As you can see in the diagram, we have an application running on top of an operating system being hosted on server A. That is an active server that handles every request to the application. We also have an identical server running the same application, which is a standby server. This is idle. It doesn't handle any requests. It just waits for a failure to happen so that it takes over and handles the requests from there on. So, for example, if there is a hardware failure in server A, then a failover is performed and the previously redundant server becomes active, therefore handling all the requests. That's a really common high availability model. If we look at a typical enterprise application, we don't just have 2 servers. We have many more servers. So this could be the deployment diagram of your enterprise application. Here we have 8 servers, but only 4 of them are really doing something useful. The other 4 are just consuming electricity. They're consuming energy while being idle. They're not doing anything useful. We see here a great potential for us to reduce our carbon emissions by 50% if we could come up with a different high availability model that takes out all these redundant servers. When we talk about servers nowadays, we mostly mean virtual machines. Let's look closer. Virtual machines usually consist of the operating system and the application with all the dependencies on top of the operating system. That's why they have a size of several gigabytes. When we start up a new virtual machine, it usually takes some minutes for the virtual machine to be up and running. On the other hand, we have containers, which are more lightweight compared to virtual machines. They have a size of orders of magnitude smaller. It's megabytes versus gigabytes for virtual machines. And whenever we start up a new instance of a container, it usually takes some seconds for the container to be up and running. That's why until today we have been forced to have a redundant server up and running. Because if we had to start up a new virtual machine for a new server, in the case of failure, it would take us minutes until the new server would be up and running. And our customers would notice that the system would be out of order. Whereas with containers, let's have a look. If we deploy just a single container, nothing standby, we don't have a standby container. We have only one active container that serves all the incoming requests. If this container fails, we can quickly create a new instance. We can spin up a new instance of a container. That means we don't have to run any redundant instances. Therefore, we can build more energy efficient applications that have a smaller carbon footprint. So remember, there is a great potential for you to save up to 50% energy just by re-architecting your application from a virtual machine to a container model, allowing you to adopt a more efficient high availability model. Let's have a look now at long-lived applications that are mostly idle. You can see here a clock where with red color we show all the time that our application is idle, waiting just for an event to arrive so that some data related to this event can be processed. With green color, we show the time on the clock where our application is really running, doing some useful processing of the data. It is evident that this type of application is not energy efficient. All the time that it's running, consuming electricity, it doesn't do anything. How could we improve this? There is a new paradigm today, the one of functions as a service. This is also known as serverless functions, where we can decompose our application, decompose our monolith into smaller functions that each one of them is short-lived. So whenever we have an event arriving, only then do we spin up new instances of these functions, process the request or the event, and then our application, our functions are being shut down. Therefore, we optimize the usage of compute resources with this new model. Functions are usually triggered by events like HTTP requests, events like a file upload or a file modification, new messages arriving in a queue, or tasks that are scheduled to run at a given time, like cron jobs. As you can see, this is a fine-grained model that allows us to build more than one functions, with each one function having a single independent functionality. In Azure, Azure functions allow us to run our code as functions without having to manage any servers. This is what is called serverless computing model. As explained, this allows us to build more energy efficient applications since our code consumes energy only when processing requests. Our energy impact, our carbon footprint, is scaled down to zero when our code does not execute. Azure functions support the languages shown here, such as Java, C#, F#, and so on. As you can see, the order here is not an alphabetical one, but it surely isn't a random one either. Can you guess why we have this order here? Stay with me and we'll explain this in a while. Azure Container Instances is another service provided by Azure that provides more flexibility than Azure Functions, because we can run any application, any code written in any language, as long as it is packaged in a container. This model supports also long-running tasks, that is, code that can run for days, weeks, or even months. But the similarity here is that we can have Azure Container Instances execute only when an event arrives, and when we don't need them, we can just kill them. Whenever we start a container instance using Azure Container Instances, there are some default values assigned about the 1 core CPU and 1.5 GB RAM per container. If our application doesn't need to reserve this amount of resources, then we can adapt them so that we maximize the utilization of compute resources. If your application needs only half gigabyte of RAM, then please do adjust the amount of resources that you reserve in order to reduce the carbon footprint of your application. What we need to remember is that we can maximize the utilization of compute resources by re-architecting long-lived applications into short-lived functions, by leveraging Azure functions and Azure container instances. It's time for a poll. What is your favorite programming language? Please grab your phone, your mobile phone, scan the QR code, and tweet your answer. Have you ever wondered how much energy is consumed by your favorite programming language? There are different types, different categories of programming languages. There are compiled languages like C and C++. There are languages running on top of virtual machines, such as Java and C#. And there are also interpreted languages like JavaScript, Python, Perl, and Ruby. Can you guess which type, which category of languages is more energy efficient? Please tweet your answer. Don't be shy. According to research, to academic research, compiled languages tend to be the fastest ones and most energy efficient ones. In this table, you can see the list of languages. The first one is C, which is the most energy efficient one. The amount of energy consumed has been normalized. So the first one, C, consumes 1 joule in order to solve a problem, whereas the most energy consuming language is the last one, Perl, which consumes approximately 80 times more energy compared to C. This is a very interesting way to look at programming languages, depending on the energy consumed. And it's impressive how big differences there are from the most energy efficient language to the least energy efficient one. With this knowledge in mind, what can we do? Do we need to rewrite from scratch all our applications in the most energy efficient language like C, Rust, or C++? We don't have to do this. The important thing is to identify the energy consuming components within our applications. As long as we build modular applications, we can identify these modules, these components that are the most energy consuming ones, especially when we talk about internet scale applications being used by millions or billions of users, then these should be the center of our attention. In that case, yeah, we should go ahead and rewrite them in an energy efficient language. Let's focus on Java. Java has been around for more than 25 years, and it's one of the most popular languages for writing enterprise applications. According to research by JetBrains, according to the survey that they ran last year, Java ranks as the second primary language used by professional developers. Interestingly, only 75% of them still use Java 8, whereas the latest release of Java is Java 16 as of March 2021. So there seems to be some tendency not to migrate to the latest Java version. What can we do, especially for Java applications, to make them more energy efficient? The first thing we can do is to upgrade our programs to use the latest version of Java. For example, since Java 9, the memory allocation model for string objects has been enhanced, and especially for Latin characters do not use 2 bytes for each character, as it used to be the case up until Java 8, but they only take half memory, using 1 byte per Latin character. This change in Java 9 and onwards results in improved memory footprints, smaller memory footprints, and performance improvements of up to 10%. I don't want to bore you with too many details. You can refer to the article that I've written here, which provides more details. Likewise, since Java 10, there is a new feature called class data sharing that is particularly useful for many applications running on the same host, like microservices that are built on the same Java stack. Instead of having each individual microservice load the same classes again and again in memory, all these microservices share a common cache where they load all the class data, and therefore we can reduce memory footprint by 15%. Again, there is an article I've written on this topic that you can refer to for more details. What we need to remember here is that by upgrading to the latest versions of Java, we can reduce the consumption of memory, improve the performance, and therefore reduce the carbon footprint of our applications. Another thing we can do is to use a lightweight virtual machine. There are 2 types of virtual machines nowadays. It's Hotspot and OpenJ9. Hotspot is the most popular one. It's the one introduced by Oracle, whereas OpenJ9 is the virtual machine introduced by IBM, which now belongs to Eclipse Foundation. Here is an experiment that I've run with a popular Java application called the Spring Pet Clinic. This is based on Spring Boot, where we can see the memory consumed by Hotspot versus OpenJ9. As you can see, OpenJ9 consumes less memory compared to Hotspot, enabling us to host more applications on a given server, therefore achieving higher density, higher utilization of the provided compute resources. And again, it's more energy efficient and can help us reduce our cloud bills by using less resources. What I want you to remember is that if you have Java applications, there are 2 simple things you can do. First one is to upgrade to the latest version of Java, and second one is to choose a lightweight Java virtual machine like OpenJ9. These are simple things that you can do even to legacy applications with minimum effort. For applications that run on the cloud, we all know that the bills that we have to pay at the end of the month to the cloud provider depend on the resources consumed. First parameter is the network traffic. How much network, how much gigabytes, for example, of traffic are we producing? And then it's about the resources we use, the CPU and RAM we use, and the period of time for which we use them. Clearly, the less money we spend on cloud bills implies that the more energy efficient our software will be. Think of this as a rule of thumb. You know, in most cases, if you achieve to reduce your cloud bills by reducing your resources, that means you have a more energy efficient software application. Azure Well Architected is a framework that provides a set of best practices. It's some kind of test, you know, they ask you some questions and you answer if you follow these principles, these practices or not. And then you get a score. In my case, for example, it was a critical one. If you have a critical score, if you get a critical score, then you have room for improvement. You can take more actions to reduce your cost, to improve your performance, and in most cases, these actions will result in more energy efficient applications. So I strongly encourage you to take this test, to follow the best practices suggested by Azure Well Architected. And in most cases, they will help you build sustainable software, reduce your carbon emissions. Let's summarize all the actions that we have proposed here. All these are actions that you can take, immediately. Some of them are really easy to achieve. First one is related to Java applications. Just by upgrading to the latest version of Java or switching to a more lightweight Java virtual machine, you can make the difference. Second one, reduce the data transferred over the network. It can be as simple as compressing your data or eliminating data that is not being used by your application. Third one, adopt an energy efficient, high availability model. That may require a bit more work because you have to containerize your application. But again, remember, it's containers versus redundant servers. You have here the opportunity to make a big win by eliminating half of your servers in your data centers. So it's more effort that you have to put here in terms of development, but there are also bigger gains. You can also identify long-lived applications and break them into short-lived functions. Again, the concept here is to maximize the efficiency of the compute resources that you use. Last thing is to rewrite components in a more energy efficient language. Remember, compiled languages are the most energy efficient ones, whereas interpreted languages consume a lot of energy. An overarching practice here is reducing the cost of running your applications on the cloud. If you manage to reduce your cost, you are likely moving into the direction of building more sustainable software. So what actions will you take in order to help prevent climate change? Please grab your phone, scan the QR code, and tweet your answer. These are very simple actions that we can all take. When you go back to work, you can just take your first step. What will this be? Please don't leave. We'll be waiting for 1 minute for you to tweet your answers. And we also have some gifts to give away from the organizers of the conference. Thank you very much for joining, for attending the presentation. Follow me on Twitter and please do visit my blog to read more on these topics. It's called axis.dev. And here are the gifts from the conference organizers. Please let me know if you have any questions. Open your microphone and we will be answering any questions you have. Do you have any questions? Was there something that grabbed your attention, something that you've never heard before?